This research paper introduces a novel computing framework that integrates flow-based programming, FBP, and large language models, LLMs, to enable just-in-time programming, JITP. JITP empowers users to actively participate in the development and automation process by leveraging their task-time algorithmic insights, regardless of their programming expertise. By seamlessly integrating LLMs into the FBP workflow, users can request and generate code in real time, facilitating dynamic code execution within a flow-based program. The concept of JITP is motivated by parallels with just-in-time analytics, which enables end users to query and interrogate data directly to build analytical products with timely and relevant insights. Similarly, JITP aims to bridge the gap between traditional programming methods and dynamic user tasks by allowing users to implement algorithms during task execution. This approach centers around empowering users to engage in programming and task automation during task execution, rather than relying solely on pre-designed software solutions. The JITP paradigm enables users to take on a central role, regardless of their programming expertise or experience level. Novice users benefit from a user-friendly and accessible entry point into programming, while experienced programmers can leverage JITP to rapidly prototype, test, and refine their algorithms during task execution. By fostering a more inclusive computing environment, JITP bridges the gap between users and developers, encouraging users to embrace their algorithmic insights, regardless of their programming background. The framework's potential is demonstrated in automating tasks, orchestrating complex data workflows, and accelerating software development. By integrating FBP and LLMs, JITP enables users to implement algorithms during task execution, facilitating dynamic code execution and rapid prototyping. This novel approach has significant implications for the development of more inclusive and user-centric computing environments. Computing paradigms, such as procedural, object-oriented, and functional programming, provide a conceptual framework for solving computational problems. Just-in-time programming, JITP, takes a task-oriented focus, where users concentrate on tasks and their subtasks, with task completion as the primary goal. During task execution, users envision algorithms to complete subtasks and improve efficiency. JITP enables the immediate implementation of these algorithms, leveraging the user's insights and enhancing task completion in real time. JITP offers several benefits as a computing paradigm, including dynamic and adaptive computing, user empowerment, increased productivity, improved task understanding and innovation, flexibility and adaptability, rapid prototyping and iterative development, and enhanced error detection and debugging. JITP represents a user-centric computing paradigm, empowering users to implement algorithms and develop tasks during task execution. To achieve mainstream adoption, a framework is needed to provide a structured approach to building software applications and accommodate any required computation. The integration of flow-based programming techniques and large language models provides an ideal JITP computing framework. Flow-based programming offers a structured, modular, and reactive workflow model that aligns well with the dynamic nature of task execution and algorithm implementation. Large language models allow for the expressive capacity to represent and manipulate any computable function. The combination of flow-based programming and large language models allows for the definition of a general-purpose, Turing-complete programming environment. The principles of flow-based programming include component-based design, emphasizing modularity, reusability, and reactive processing. The execution of a program is driven by the flow of data, rather than being strictly controlled by a predefined sequence of operations. Flow-based programming, FBP, and large language models, LLMs, are integrated to create a framework for just-in-time programming, JITP. FBP's modularity, reusability, and scalability, achieved through its component-based design and reactive execution model, align well with the JITP approach. LLMs leverage language understanding and code generation capabilities to enable users to express algorithmic insights and automate tasks in real time. The proposed JITP framework implementation involves identifying task-specific LLMs that align with programming language or task requirements. LLM components are then defined within the FBP framework to encapsulate the complexity of interacting with LLMs and provide a simple interface for other components. Data flow between LLM components and other FBP components is established, determining input data required by the LLM component and defining outputs from the LLM components. The reactive execution model of FBP triggers LLM interactions based on incoming data or events, such as generating code that is integrated into the overall execution workflow. This integration combines the capabilities of advanced language models with the modular and reactive workflow of FBP, creating a powerful environment for JITP. By leveraging FBP's reactive execution model, LLM interactions are triggered in real time, enabling users to express algorithmic insights and automate tasks efficiently. The resulting JITP framework enables the creation of dynamic, adaptive workflows that can be easily modified and extended. The proposed framework offers a novel approach to JITP, enabling users to harness the power of LLMs within a modular and reactive workflow. The integration of FBP and LLMs provides a scalable and efficient solution for automating tasks and expressing algorithmic insights in real time. The integration of large language models, LLMs, with flow-based programming, FBP, in a just-in-time programming, JITP, framework is a novel approach to software development. This integration involves 7 key steps: defining a JIT code generation module, handling LLM state management, and iterating on improvements based on user feedback and performance evaluation. A cutting-edge platform, the Composable Data Ops platform, developed at MIT, exemplifies this integration. Composable combines FBP and LLMs into a robust JITP computing framework, providing a structured environment with predefined components, tools, and libraries for building software applications. By incorporating FBP principles, Composable offers a visual and intuitive environment for designing and orchestrating complex workflows. This enables the identification of bottlenecks, optimization of performance, and ensures maintainability. A key component of this platform is the JIT code generation data flow, which serves as an app reference module within other data flows. This data flow consists of a web client robust module that accepts a single string input as a prompt, makes an HTTP request against the ChatGPT API, and returns the response. The web client robust module utilizes specific parameters, such as the URI for the OpenAI's ChatGPT API, and can be extended to utilize other purpose-built LLMs. Composable's modular design allows users to compose unique dataflow applications by dragging and dropping modules and connecting them together in an infinitely configurable manner. This flexibility enables the handling of all data types and consumption of all data sources, making it an ideal platform for integrating LLMs with FBP in a JITP framework. The implementation of a JIT code generation dataflow using Composable's FBP framework is discussed in this section. This dataflow interacts with an external API to generate and execute Python code based on user-defined prompts. It involves sending a POST request with JSON content, including the prompt, and then extracting the raw code from the response. 3 examples of just-in-time programming are presented: simple arithmetic operations, a primality test, and a Boolean primality test. Each example utilizes the JIT code generation dataflow as an app reference module within a new dataflow, allowing for the creation of a more complex workflow that integrates multiple functionalities. The first example demonstrates how to add or subtract 2 integers using a simple just-in-time programming dataflow. The prompt is used to generate Python code, which is then executed with 2 given inputs. The results of the execution are displayed for both addition and subtraction operations. The second example showcases a dataflow that checks if a given command line integer input is prime. The prompt is used to generate a Python script, which is then executed with an input of 31, confirming that 31 is prime. To make this dataflow more integratable with other dataflows, the prompt is adjusted to return a Boolean value, 0 or 1, indicating whether the input number is prime or not. The revised just-in-time code and the full dataflow with execution results are presented in Figure 8 and Figure 9, respectively. Overall, This section highlights the flexibility and power of the JIT code generation data flow in creating complex workflows that can interact with external APIs and execute dynamically generated code based on user inputs. The authors demonstrate the capabilities of just-in-time JIT programming using a large language model, LLM, through 2 examples. In the first example, the LLM generates a primality test, taking an input and producing a JIT code snippet to determine whether the input is prime or not. The data flow and generated code snippet for the original input are illustrated in figures 6 and 7, respectively. When the input is revised, the LLM generates a new code snippet, shown in figure 8, which is executed accordingly, as depicted in figure 9. In the second example, the authors showcase the ability of JIT programming to generate new data. Given a prompt to create a pandas data frame called _composable_table_out_ with a column _state_ containing all U.S. states that border the ocean, the LLM generates a Python script, shown in figure 10, which creates a data frame with the required information. The resulting data flow and table output are displayed in figure 11. The generated code snippets demonstrate the LLM's ability to create functional Python scripts. The first script defines a function as _prime to determine whether a given number is prime, while the second script creates a dictionary of U.S. states and their ocean borders, filters the dictionary to include only states that border the ocean, and displays the resulting data frame. These examples highlight the potential of JIT programming using LLMs to generate code snippets that can be executed immediately, enabling efficient and dynamic data processing. Table manipulation is a critical aspect of complex data processing workflows. To demonstrate this, the authors utilize just-in-time programming to generate a new data table. By providing a prompt to select only records that appear more than once in an input table, the generated Python code is illustrated in figure 12. The data flow and results are depicted in figure 13, showcasing a table with duplicate records being passed in, and only the duplicate records being retrieved. The authors emphasize the importance of ensuring trust in software development, particularly in a just-in-time programming paradigm. Trust is defined as the code performing its intended functions correctly and predictably, delivering accurate results, responding to inputs appropriately, and operating without unexpected failures or errors. However, when a language model, LLM, generates raw code, ensuring trust is challenging, as it requires expert programmers to review, check, and test the generated code. To address this limitation, the authors propose leveraging the Composable and Flow-Based Programming (FBP) framework to generate complete, visual, flow-based programs. This approach enforces strong typing of modules and promotes loose coupling between them, providing features such as visualization of control flow, clear representation of data flow, and easier comprehension of the program's logic and control structures. By generating flow-based programs just in time, the authors enable easier understanding of the program's intended behavior, reducing the likelihood of errors and improving accuracy during development and debugging. The FBP framework allows for the visualization of control flow and data flow, making it easier to comprehend the program's logic and control structures. This approach also promotes loose coupling between modules, enabling easier modification and maintenance of the program. By generating visual, flow-based programs, the authors ensure trust in the generated code, providing a graphical representation of the program's control flow and data flow. This enables developers to better understand the program's intended behavior, reducing the likelihood of errors and improving accuracy during development and debugging. Visual flow-based programming offers several benefits, including explicit representation of data connections and transformations. This clarity ensures correctness, identifies potential issues or bugs related to data handling, and reduces the potential for underlying errors in required functions. The intuitive and visual representation of the program also reduces cognitive load on developers, making it easier to understand complex logic and relationships between program components. This leads to fewer mistakes and better accuracy during development. Debugging visual flow-based programs is simplified, as the graphical representation allows developers to visually trace the execution path, track data flow, and identify problematic areas. This ease of debugging helps identify and rectify issues more efficiently, resulting in improved correctness and accuracy. The paper illustrates this concept with a simple dataflow example that takes two integer inputs, performs an arithmetic computation, and returns an integer output. The dataflow consists of three modules: two external int input modules, a calculator module, and an external int output module. This visual flow-based program can be converted into structured source code using Composable's Fluent API, a set of C classes that interact with composable services. The paper demonstrates how the large language model, LLM, can be trained to generate new data flows. For instance, given a prompt to enhance the original data flow, the LLM generates a new program that takes two external integer inputs, feeds them into a calculator module for addition, then feeds it into another calculator module along with a third external integer input for addition, and returns an external integer output. The generated output is shown as both code and a visual data flow. The code snippet generated by the LLM represents the new data flow, which is built using the Fluent API and Composable services. The generated code includes the necessary using statements, namespace declarations, and class definitions to create a functional program. Just-in-time programming, JITP, is a user-centric approach that enables algorithm implementation during task execution, empowering users to leverage their algorithmic insights in real time. By integrating flow-based programming techniques with large language models, JITP facilitates the expression of algorithmic insights, automation of tasks, and rapid prototyping of software solutions. The Composable JITP platform is a state-of-the-art framework that seamlessly integrates these principles, demonstrating versatility across various domains. In data science and analytics, users can utilize large language models to generate code for data preprocessing, feature engineering, and model evaluation, while orchestrating complex data workflows with flow-based programming principles. This enables efficient data pipeline management, reducing the time and effort required for data preparation and analysis. In software development, the Composable JITP platform facilitates rapid prototyping, automates repetitive tasks, and allows for the development of large, microservices-based architectures. Seamlessly integrating large language model-generated code within the larger codebase, the platform enables efficient software development and deployment. The Composable JITP platform also demonstrates its applicability in natural language processing, machine learning, and robotic process automation, empowering users to implement tasks and subtasks in real time. By leveraging algorithmic insights and large language models, users can rapidly develop and deploy complex solutions, revolutionizing the way we approach programming and software development.